Okay, this is the Latin American network of condensed matter physics. This is the Saturday seminar. This Latin American network includes the universities, the Universidade Nacional Maior de San Marco, em Peru, Universidade Federal de Pernambuco, em Brasil, Universidade Federal Rural do Rio de Janeiro, em Brasil, Universidade Nacional de Colômbia, o Centro de Investigação e Estudos Avançados em México, Universidade de Zulia, em Venezuela, Universidade de San Sebastián, em Chile, Universidade Católica del Norte, em Chile, Centro de Investigação em Materiais Avançados em México e Universidade Federal Fluminense, em Brasil. The talk for today, our invited for today is Antonio dos Santos. Is our great friend of mine for several years, decades ago. We met here in Aveiro, in Portugal. He's a great friend of mine. He's also my co-worker, and it's a great pleasure for me to have you here, Antonio. And thanks for you to accept this invitation. Antonio graduated in materials engineering in Lisbon, and then he did the PhD in University of California in Santa Barbara, and then returned to Portugal for a postdoc when we had this opportunity to meet here in Portugal. And then he returned back to US when he leads a beamline of high pressure experiments in the spallation neutron source in the Oak Ridge National Lab in Tennessee. I don't know if I lost something from your path, Antonio. Sorry for if I lost something. And thanks for this opportunity to have you here. Go ahead with your presentation, Antonio. Thanks.
Okay. Well, first, let me thank Mario for the kind presentation. Also, I'd like to thank the whole network, the LAFMAT network. I think is really powerful to work together across science areas and borders, and so working at a large facility, and I'll address this collaborative spirit that I feel really at home. Not for my roots, I'm Portuguese, I'm not Latin American, but I certainly share the heritage, but also because of the way we do science here. I think it's really close to the way that you are really striving to do science there. And I hope that we can keep this collaboration, and you find this a very lengthy business card, an introductory card, but I hope this is the beginning and it doesn't stop later this morning. So as Mario said, I work since 2007 in Oak Ridge National Laboratory, which is it has a really noble history. Well, I wouldn't say noble necessarily for everybody, but it started as part of a Manhattan project. And it was from the beginning, it was called Clinton Laboratories because there's a Clinton town nearby. And it was actually a secret city of 15,000 people, which was aiming at purifying plutonium. So it's really, really in the advent of the nuclear age. It was recognized that if you needed plutonium and other isotopes, we needed a continuous operating reactor. So there was experiments in Chicago with the Chicago pile by Fermi, but they were just basically starts and stops. Like they couldn't keep the reaction maintained for long periods of time. So it would be very difficult to do a continuous reaction. Now, Fermi did not want to come to Tennessee because it was just woods. It still is. But they did build here this, let me see. Okay. They built here what's called a graphite reactor. That is the first, it's still here and it's not working, obviously, but it's the first reactor in continuous operation. And the way they did plutonium is that they put these little pellets of uranium encased in aluminum, in the core. So this is concrete, but inside there's a huge cube of graphite, and you could control the reaction with temperature and by putting absorbing cadmium rods or fuel, and that could keep going and going. And as that each little hole had like a bunch of little uranium pellets, it was pushed by these rods and it would fall on the water on the other side. There was a pool, and then it would be captured from the pool. They would take the aluminum, and then they would purify the plutonium elsewhere, not exactly here, but 2 or 3 kilometers away in a different plant, as they say. Very quickly, and this is kind of why I kind of it's important for us to have an open mind, is that very quickly after the war was over, let me see, there was the war was of 45. 4 years later, they asked permission to have a hole in the reactor to extract neutron beams, and within 4 years, they were doing the structure of ice. So, in fact, this paper was instrumental in the discovery of the ice rules that end up giving a Nobel Prize for the ice rules to Linus Pauling. And in fact, this shoal ended up getting the Nobel Prize for neutron diffraction in the 90s. So Wallen didn't get it because he had passed by then, but it's probably one of the longest techniques that was clearly successful for decades before being awarded the Nobel Prize for neutron techniques. This is how the lab looks today. And so we're vibrant, we are open, there's many user facilities. It's still the largest laboratory for the whole Department of Energy complex for materials research. The focus areas are mainly here, and there's biology, environment, and clean energy. Of course, it's Department of Energy. This physical science encompasses a lot of materials and physics studies. There's some national security, not much, but there's still a big component of basically radiation-associated research, including, for instance, the headquarters for the ITER project in the United States. So that Karadash fusion plant in France, the United States contribution is being developed here in Oak Ridge. We are also home for the largest supercomputing for civilian use. So people can apply for CPU hours on the one of the first public exascale computing facilities in the world. I work in this neutron science aspect of it. Now, if you're wondering where it is, it's here. This is Tennessee, and we are kind of, I would say, close for the United States, and from Latin American, certainly Brazilian context, we're only 3 hours away from Atlanta, which is a big airport. You all can come from Atlanta. Many people arrive in Nashville, there's only 2 hours away. From DC is 8 hours by car, but it's cool. And Chicago also 8 hours. So we're not close, but we're not too far. The biggest problem is that the lab itself is still from like the big valley that was expropriated in the 40s. So if you don't have a car, you'll be having microwave food for your stay. So you do need to have a driver's license if you want to come in and out of the lab, because it's multiple miles between this location and the front gate through woods. So I will start now a little bit with my talk, which is basically I want to be very broad. It's basically neutron scattering techniques under extreme conditions. Now I keep these vague extreme conditions and how they can help materials research, and I'm going to ask you to exercise a little bit of imagination. I will primarily speak about high pressure applications, but the requirements that you need to do high pressure research is very transferable to many other extreme conditions in terms of like fast measurements, small beams, spatially resolved things. So do try to take this not as me like blowing the horn of high pressure research, but truly to see how it can map to you. There is the overview. I'm not going to assume all of you, when you see this, are very familiar with neutron scattering, so I'll go over a little bit of the fundamentals. I hope that's appropriate. I do want to say, like, why do you want to kind of push the envelope of the extreme conditions? And I'll use the illustration of high pressure, but again, like, I don't want to be too hung up on the high pressure aspect. It's just the one I know, the one I'm an expert. But I've also learned over more than 10 years here that a lot of what we do is very easily transferable to other techniques. I picked these three highlights, not because they're the most recent or the most, well, they're certainly exciting, but they're the most exciting. But I hope to illustrate different aspects of how we can then use these capabilities and these developments to really address scientific problems. And finally, I want to talk a little bit about, or throughout, future challenges, which are also opportunities. And that is kind of like our mantra, is that going to higher pressure or smaller beams is really an opportunity to collaborate and bring people in. Now, if I had to summarize this, I don't expect anybody to remember what a Shastri-Sutherland lattice is. I would like some of you to bring a little bit more from what neutrons and what they do and how you science with it. What can you do with them today? Not what you think you did, not what your advisor told you you were doing it decades ago. What is the current state of the art of neutron, specifically diffraction? And I hope, and that is really your homework, like how does this help your research? Because that's something that I will never know, right? So I would be remiss not to thank first the SNAP team. Chris is no longer with us. He went to a different path, but Jamie and now Malcolm is a new hire. We are about to get a new instrument scientist this summer, but he's not here. And some of the developments you'll see were made primarily by Rainy Bowler, which is truly like a genius in high pressure science, and Bianca Haberl, another sample environment high pressure scientist. The project that I'll present were led by Sarah Harveyfeld, which is now at Duke. Malcolm Guthrie, that is the one that we ended up capturing, but did a lot of this work while still at Carnegie Institution of Washington and the European Spallation Source, and Carl Sandman from the City University of New York. So first, a little bit about neutron scattering. Like, what is it from our side, from the material science part? First, you can produce neutron beams with wavelengths, and these wavelengths are compatible with diffraction. So we're talking about like from 0.5 angstroms to like 2 or 3 angstroms. You can really probe atomic structures of materials. To be very clear, you can make beams with much colder neutrons, in which case you're going to explore much larger scales. So you're going to have SANS, small angle neutron scattering, and mu SANS, and you can go almost to the micron level of structures. What all I'm talking about here is atomic structures, to be clear. But the big contrast with other radiation sources is that neutrons are scattered by nuclei, which means they have very different cross-section ratios between elements than when you do X-rays, which means that if you want to study a uranium carbide with X-rays, you barely see any carbon because the scattering cross-section is so much smaller. But if you have a uranium carbide, you can really know what the carbon is doing in the context of neutron scattering. So that is like maybe one of the biggest advantages is have truly a different way to contrast. And the million-dollar question, or I would say the billion-dollar question that people want to answer is, what is hydrogen doing? And you can see here, hydrogen scatters stronger than tungsten or uranium. So anytime you see a hydride question, or a bio question, or a drug delivery question, or even a polymer question, neutrons bring a huge advantage because every neutron technique will be basically weighted by this cross-section, and hydrogen really takes precedent. So that is really the reason for all these neutron facilities, to, if I say so. Another one, which is maybe less important for society, but it's critically important for us in the LAFMAT network, is that neutrons have spin. So these spins actually interact with spins in atoms, in the electronic shells. But so the corollary of that is if the spins in the lattice become ordered because of an ordered magnetic structure, this diffraction will now reflect that magnetic ordering. So the neutron diffraction can really describe or interrogate the actual magnetic structure of materials in terms of the vectorial nature of spins with respect to the lattice orientation. So you know how each spin is oriented at each location of the lattice with respect to the lattice. And that is truly unique technique that, as far as I know, None, if any other techniques give that level of detail. Another thing is that neutrons are neutral. That has two implications. You can do a lot of engineering studies without having to cut through the pieces that can lead to like relaxation, so you don't really know what's there. Also, you can make really complicated sample environments to your heart's content, and neutrons can come in and can come out, and you can still get data from your sample, provided you have good alignment and good collimation. Another thing which is also important for the LAFMAT is that they don't interact so strongly with materials, so that they don't deposit heat. So for instance, while in X-rays, as soon as you shine with a synchrotron on a protein, you basically decompose it instantaneously. You can do neutron measurements on the same protein over days and without any effect. The same thing is like if you want to do studies at millikelvin temperatures, with neutrons, you are pretty sure it stays at millikelvin temperatures, which is a challenge for X-rays, for instance, that you don't really know at where you're illuminating what is the local temperature, because X-rays will warm up your sample. Now, finally, and this is really also unique, is that neutrons can be produced with energies because of their mass that matches dynamical process of materials. What do I mean by this? Any phonons, like cooperative, like oscillations in the lattice, but also rotation modes of molecules, dynamic energy barriers for diffusion, for instance. So you can actually have neutron beams that match those, and so you can interrogate directly that energy. So this is a case of a dispersion curve in graphite. Now, one thing that I don't say yet here on these images, but I will say now, is that neutrons are incredibly amenable to simulation. And this is because they're truly like a mass particle interacting with a lattice. So as you can see here, this is a simulated data from this experimental graphite data, and you can see the detail. This is for inelastic. Also, this is a case of a simulation and experimental magnetic diffuse scattering in this cesium compound. And so this combination of like being able to do the ground state measurements along with the ease of simulation makes this really key for a lot of problems in condensed matter physics, but also throughout material science in general. I kind of wanted to add this slide to this talk because I wanted for you to see the contrast. This is what you'd measure in a laboratory. This is some random compound, like I think is a lead sulfide, and you can see it's pretty sharp, but you can see the peaks. But it decays, and this is the despacing. So this can give you a sense of like the spatial resolution. You barely have any signal left as you go out in Q at higher momentum transfer. You can see shoulders, and so you can really ascribe like the space groups, small lattice parameter distortions. Even a lab source is good for that. If you go to a similar thing, actually this is the same compound with neutrons, you see immediately two things. It has lower resolution, and I'm talking about the peak width, not talking about the image quality because it's pretty bad actually. But you can see there's a lot more intensity at high Q. And what this tells you is that although you don't see like the lattice distortion so well, when you do the Fourier transform, you have so much data to Q that when you do the Fourier transform, you have much better atomic positions and thermal parameters. So the local structure of the material is much better known. The other thing you can see is that the peak intensities are a little messed up. They're not the same. And this is because of what I mentioned. Each peak is weighted, in this case, by the neutron cross-section. Here is peak is weighted by the X-ray scattering length. So you can see here, for instance, that if it's a lead sulfide, you will barely see any oxygen. So if you have this same lattice with just with lead, you'd account for probably like 80 or 90% of all this intensity. While here, everything is much more evened out. So you can get like your oxygen positions much better, not just because of this extended Q, but also because more of the intensity on each peak comes from the oxygen. So, by the way, this might be a good time that Mario or somebody, if somebody wants to interrupt from the chat, feel free to do so. Now that hopefully I showed like a little bit what neutrons can do, so I want to move on for neutron sources. Now, let me start with the bad news, is that they invariably require large facilities. Like you can't have a neutron source for material science at your home laboratory. There are cases where you have some research with small nuclear reactors at universities, but even those are rare. And this is because it either requires fission or spallation. Now, starting with fission, you are probably more familiar, requires a nuclear reactor. This is actually the image of the pressure vessel and a fuel replacement at our reactor at Oak Ridge called HIFER. So this uses a nuclear fission. So basically there's this cascading effect and neutrons, some of them come out. But the problem is that the flux depends on the fission rate and therefore is limited by heat production. You can't have a runaway process, and also the materials can't melt. The other problem, besides the obvious political one of creating nuclear reactors, is that it creates radioactive waste. So environmental management is a constant concern throughout the lifetime of the facility. Spallation basically is a particle that impinges on a heavy atom and it spalls neutrons out. Now, if you stop the accelerator, you stop the spallation process. So there's never a risk of a runaway reaction. So typically it's pulsed, and this is because you want a higher power to get like a higher peak power, but also a higher width of neutrons, and I'll go back to later. It has a high peak intensity, and therefore the heat production is relatively low. The corollary of that is that you can see here, this is log scale, the nuclear reactors essentially since the 60s have been fairly stable for research, while the accelerator-based sources are still growing. Now, take this with a grain of salt, and the reason for that is that when you have a steady state reaction, the time integrated flux is much higher than those peak pulses. What you don't have is you don't have a time structure. So basically when you have a steady source, you have a monochromator and you keep measuring all the time at that wavelength. When you have a pulsed source, you have this big sharp peak of created neutrons, and as they travel through the instrument, you start separating the different velocities as a function of time, and until the next pulse comes out. So now you have like a whole range of wavelengths to your disposal. Now, this brings a corollary, again, is that when you work at a reactor source, you can think of a Newton diffractometer essentially as your powder diffractometer. You give you a peak shape, you give you a wavelength, and your refinement goes as planned. The machine is essentially the same as a X-ray diffractometer, a conventional one. However, in time of flight is different. Of course, you start with the same Bragg's law, but then what you have a pulsed source, a moderator that adjusts that energy spectra. Sorry to go back, if I can. This energy spectra depends on the moderator. Where you want your energies to be, you can adjust that by basically putting a box of a material, can be cryogenic hydrogen, can be water, can be methane, and that basically will slow down the neutrons so that you have a peak intensity at the energies that you want your instruments to see. So that's what this moderator box is doing. It's just adjusting that wavelength band. Now, because it's literally neutrons flying over a beamline that is multiple meters, you can define their speeds by choppers. These are mechanical disks with apertures that are spinning at the same frequency as this source, and that limits which wavelength you see. And then you measure the time of arrival on your detector, and you know at which angle of scattering. So if you have the wavelength, because you have the velocity, you have the angle of scattering, then you can do a powder pattern based on the despacing of the material. And the function is simple enough. And you can do it because the velocities are quite classical. We're talking about milliseconds to microseconds, depending on the length of the beamline. No. So these are large facilities and they're expensive, but they're still being made. And this is just a case of like the ISIS in the UK just invested in a second target station recently. Japan also in the 2000s, in the mid-2000s, started the MLF, the Materials and Life Facility, again with a spallation source. The Chinese also started more recently, I believe already in the 2020s, the Chinese spallation neutron source, and the Swedish will start in a few years, the European spallation source. Of course, given this audience, I have to bring up, there's of course the Argentine Reactor 10 and the Reator Multiuso Brasileiro, which is a project that will bring truly state-of-the-art not only neutron scattering facilities, but isotope production and other techniques to Latin America. And I think I can speak for all of us, including us here in Oak Ridge, that we're really excited to see such new facilities coming online when it happens, which to the best of my knowledge, there is no defined date yet, but I know there's been projects for many years to make this happen. Of course, we can't be behind, right? Sorry for the Portuguese, but parar é morrer, like to stop is to die. And there's also upgrades at ORNL. So we are undergoing now a proton power upgrade to go this accelerator to 2 megawatts of protons. Just a little nuance, because you're doing time of flight, we want the sharpest possible pulses. And that's why after this accelerator, we have this accumulator ring, and what it does is it collapses all these protons into bunches. And they keep accumulating, that's why it's called an accumulating ring, but it's also shrinking in time. And when they're finally deployed to for this target station, you have like this really intense proton pulse hitting a Mercury target, and that is creating neutron. The HIFER, which is our other reactor, is working since the 60s and is due for some upgrades. More imminent is a beryllium refractor replacement, but what we really like to do is a pressure vessel replacement that would allow us to measure neutron scattering at a world-class facility for decades to come. As is, we don't have decades anymore because it's just an old reactor. And of course, we are also trying to do a second target station. We will basically use the same accelerator. So this will then run at 2.7 megawatts, but 700 kilowatts of those will go to the second target station, which is more for colder neutrons. Again, this is just a project, but looking to the future, you don't make $1 billion investment without like an expansion plan. So this length, which is 1/4 of a mile, so it's about 400 meters of accelerator, already had gaps in these superconducting chambers to increase power so that we can service this second target station. Okay, so this is kind of the part that I had for neutrons. And I want to kind of ask, right, the metaphorical question, like, why do you need materials at extreme pressure? And like, I don't really think I need to spend that much. Is that you can make new phases. You can have new properties from these phases. You can have super hard diamonds or basically a layered compound like graphite or graphene. An interesting one is that you can access to perturbations, as you can see here, far greater than temperature or magnetic field. As you can see, the free energy change with accessible pressure is much higher than what you can do by the time you vaporize your material. The other thing is that you can do all these perturbations with pressure is near the ground state. So that is a real good advantage for people who are thinking in a more fundamental physics of like trying to tune Hamiltonians, that you can really change the density and see what the implications are and then go and measure. This is true in the chemical sense, like when you're doing manganides in the early days, people were doping everything, and so you never really know if it's disorder, if there's inhomogeneities in the material. The reason why I make this not really true is that sometimes when you apply pressure, you have to be very careful if it's truly hydrostatic or if it's not. And depending where you are, you can start adding shear stresses. So you may change the material's properties with pressure. So this is not an absolute free. The other thing is that it's very amenable for modeling, in part because you can make measurements at low temperature, and because basically the density of the material is basically, you just type a new unit cell volume, and then you see how the system converges. So it is really a wonderful playground for physicists like us. I'd like to say that sometimes, this is not always, allows the study of dynamic phenomena. There's clearly shock physics fields, response to impact on like glasses and other structural materials. Studies on indentation have found new materials in like silicon and germanium. This is clearly not pressure, but it's pressure adjacent. And also assists in real world problems, like some planetary science, like ice clathrates in the bottom of the ocean, the development of new super hard materials, the consequence of hydrogen embrittlement, which is important for hydrogen economy, improved gas storage. So there's a lot of areas, and you start seeing here already that pressure here is basically many things. You don't have to be at 100 GPa all the time. A few kilobars in an application for society can be already fairly high pressure. Sorry, I meant to the, and this is an example of how even the simpler element can go from BCC at room temperature, only has three solid phases, and then liquid. As you increase pressure, this is the number, 9 lithium phases so far. And some of this variability may imply that it's a quantum phase, this lightness of lithium that allows for all this structural zoo of different phases, including some superconducting ones. So this is a little bit why like pressure in extremes can be exciting, and you never really know, nobody could predict probably that you find this many structures in such a simple metal. Now, the coupling of high pressure then with neutron is always a compromise, right? So I went over the little like bullets of why neutrons are important. But as I said, like it's lower flux than X-rays, synchrotrons, even Ramans. They have a weak cross section, so it's longer measurements. The resolution is not the best, and sometimes requires large samples, although this is the caveat. When you start adding a high pressure, because you need large samples, you can't go to such high pressure. And because it's so intimately coupled with the pressure cell, often in your data, you see the signal from multiple phases, from the cell body, from different sample containers. At these large samples, it's very difficult to get truly hydrostatic. So you often lose sample quality when you do deviatory stresses. And you require large pressure cells, which are both expensive, but also longer time to cool and to heat up or to warm. And so it makes these experiments really challenging. But there are good reasons why we want to go that route. And I'll go a little bit forward here. Anything with hydrogen bonded, water, ice physics, methane, many clathrates, clathrate hydrates, any hydrogen bonded systems requires high pressure neutron. To know when materials are made or why they're not being made requires in situ monitoring, and neutrons are great for that. Studies of gas cell systems, because as I said, the extended Q allows you to see the vibration of these guests in these cavities. So it's great. That extended Q also allows for the studies of melts and glasses at high pressure to replicate what happens in planets. This is then coupled to the isotopic sensitivity of these light elements in mantle materials. There was gas storage for the hydrogen economy, and more relevant for us, the direct magnetostructural coupling, like as you change the structure, how is the magnetism changing? And also, of course, quantum phenomena, where you can really stay at very low temperatures and basically use neutrons to interrogate both these magnetic phases and these superconducting phases. And in this case, is a uranium-germanium, where any other technique not only would warm it up, but basically uranium would dominate the signal. And here you can truly see how the whole structure is behaving. Now, this is certainly not new. Why we need high pressure and neutrons. And it was actually recognized almost at the same time as the time of flight of method was kind of developed. And this Brugger said that this method has been developed as it's compatible with geometrical restrictions of pressurized samples. And indeed, it was easier days. Within years, the first high-pressure diffractometer was built on a reactor, but using a pulsed source. That's that chopper here. And there's a little pressure cell. And within 2 years, they were asking for more intense neutron beams. And this struggle is going on today, as I showed you earlier, with the ongoing proton power upgrade for us and for many other facilities. Now, you can see that when you have a time-of-flight instrument, you can really want to do pressure work. And this remains true. So the ISS facility, the time-of-flight, has its own high-pressure dedicated diffractometer. Planet is at the MLF in Japan. We are here at the SNS. We have SNAP. Earlier than this at LANS, which is no longer in the user program. There's a HIPPO, which is that HIP is high pressure dedicated. And looking forward, the Chinese spallation neutron source has an approved instrument which is being built, and the ESS in Sweden has an Expositor project that did not get funding for the first round of instruments, but there is a plan to use a downstream station to have a high pressure analog of this ready to go sooner than a dedicated port for high pressure research. So this is just to illustrate how high pressure neutrons is truly coupled and has been for decades. Now is the time to go over some examples. The first one I chose because it really illustrates what you gain from powder diffraction and neutron diffraction at high pressure. Just a little bit of the science. The Chassis Sutherland developed this model of orthogonal dimers where there's an exchange inside the dimer and another exchange between dimers, which is symmetrical. So each dimer end couples the same way to the other dimer in this triangular fashion. It also assumes that the J double prime, the interlayer, is very negligible. And what is interesting is if you start in the computer tuning this J prime over J, if it's too strong, if J is too strong compared to J prime, you have dimers. That's a trivial solution. If it's very much the same, then you have long-range antiferromagnetism. But there's a sweet spot where it is frustrated. And we were lucky because chemists come up with this strontium copper borate, which is tetragonal in ambient conditions. It is non-magnetic and has a single ground state. And it's pretty much a prototypical Chassis Sutherland like realization in nature. And so it was really interesting to know what would happen as you change pressure. How are we playing with this J over J prime? Earlier work with X-rays knew that was like a phase transition. And we came and did some neutron work in powder. But the question is, if you're breaking this frustration, does anybody really believe that this is magnetic peak? Like, it will be a very hard sell. So what we did is that we measured single crystal on the same crystal as that. Now, this pressure cell only allows in-plane scattering. So this is really all you have is this HK plane, but you can see that in single crystal, every spot shows up and is resolved. And this is the advantage of time-of-flight neutron, is that this is a single configuration of the instrument. There's no rotations, the cell is static, and you get all this information with two detectors. Now, this is why Brugger was saying this time-of-flight technique is really compatible with the confined geometries of pressure cells. Now, the other thing that you get with single crystals is that we have a huge increase of sensitivity. So it's not visible in this plot, but if you know where to look, you can see here the scale is 2,000ths of a neighboring nuclear peak of the, I believe is the 040. And this, we could demonstrate that the 030 would appear at high pressure and it does disappear at room temperature. So this is the magnetic structure. So we broke the Sutherland frustration, and we're probably in the regime of this long-range order. Now, unfortunately, or fortunately, we had the powder data, and that allowed the solution of the structure, the refinement of the structure. And what we found is that we kind of left the Chassis Sutherland approximation. And what we did is that we bent the dimers out of plane, and that basically the model doesn't apply. So we are truly seeing an antiferromagnetic order, not because of the J over J prime being changed, but because we intrinsically changed the structure with this pressure. And this is something we wouldn't be able to do without neutrons. The next cell is going to be an illustration of the challenges for the using ultra high pressures. Now, some of us are familiar with the X-ray diamond level cells, right? Samples are about 100 microns by 30 microns thick, and these are common at X-ray sources. But these are much less common at neutron sources because to see, you need to increase the sample size by a great amount. Now, we have developed that in Oak Ridge, and this is what a pressure cell looks like. You can see it's very beefy. And because of this large culet, you really need a press to increase pressure. You can't do it with screws anymore. For scale, this is about 5 centimeters, and this is about maybe 8 centimeters tall. So this would fit in your average coffee cup, at least an American coffee cup. The way we measure is through the axis, and the beam goes like this through the diamonds and scatters at 90 degrees, unlike on X-rays. And one advantage is that now I have these single crystal spots here, and the powder signal is dispersed over the detector. This is another illustration of the higher sensitivity. Like, you wouldn't know there was a single crystal peak there, but there is. And you know this because if you know the unit cell, you can index and you can go and search not only in area, but also in time of flight, where the peak would be, and indeed it is there. One problem is that as the neutrons come, they go through this big single crystal, which basically monochromatizes some wavelengths of this incident spectrum of neutrons. And another problem is that as you increase pressure, the strain on the diamond changes. And so this almost removes completely any wavelengths like this. So it's very difficult to analyze this data as a function of pressure because you have to take into account this transmission data as a function of pressure, which has to be collected in situ, and that's why we have this monitor here. I just want to go here to say that this is actually, even though it's water, is a complicated refinement because the angle of the water, of the hydrogen or the deuteriums in water is different than the tetrahedral coordination of water in ice. And so you have a lot of atomic disorder, both on the deuterium, on these 3 possible positions, and the hydrogen in these 6, the oxygen in these 6 possible positions. Despite that, this is how good of a refinement. This is at 12 GPa, but it's pretty consistent, and you can refine all the way down to 0.8. If you remember, the original powder pattern I showed you was stopped at 1. We can go to 0.8 angstroms in the spacing at over 10 GPa in water. And what we're looking for increasing pressure is like, is there a point as this hydrogen stays in the middle of the bond and water becomes essentially ionic solid? It has a name, it's called ICE-10. It's never been observed in the lab yet. There has been calculations, and this is just a contrast. So if you consider a purely classical or a quantum system, where would the centering happen as a function of essentially pressure? And this was the prior known structures of water. So we're very far, the low pressure ice, we're very far from this regime where you can start seeing these contrasts. This is the same I was showing you. And by extending it to 60 GPa, these neutron measurements, you could see you start classical. It does seem that as you approach the centering, you do have to account more for the quantum aspect of the hydrogen, which is not surprising. Now, if you go here, as I said, we did refinements up to over 60, just shy over 60. If you extrapolate, you know that you get to ICE-10, which is this ice where the centering, at about over 100 GPa. Unfortunately, that has been, what's it called? That has not been achieved yet, but we're still trying. Now, for the interest of time, and because I really would like to give opportunity for questions, I'm going to jump over my next third example. Is a work I did with Mario, so maybe another time I'm invited, or me and Mario will talk about this. Is about barocaloric effect, which is a much lower pressure. So I do apologize for this, but I do want to go a little bit what we want to do next. We do want to have different diamond anvil cells. As you see here, we do want more reciprocal space coverage. Different anvils which are cheaper, and now they're coupled vertically so they can be spread over many instruments. We want to change pressure in clamp cells, which we have already achieved in situ. So now you can go to 22 GPa, but instead of taking this out for every pressure change, now we can do tens of pressure changes at the same temperature on the same crystal. And of course, we're always improving not only the accelerator, but at the instrument. And this is the result of a recent improvement with a new guide. And this is a really homogeneous single crystal peak. And this is what you can do from even from our snap detectors, which are not a huge angle coverage. You have a lot of information from your crystals that you can integrate because the peaks are so well behaved. Another thing we want to do is use the lessons learned from using such small beams to then measure really small measurements of pressure recovered samples or other rare materials. So this is samples recovered from a laser heated DAC, and this was a single crystal diamond chip that would help us to know that we are really shining on the right spot. This little holder is only like 600 microns in diameter. This is technetium, which is a unstable isotope, so you really don't want to handle a lot of it. And this is the powder pattern of this small piece of technetium in our beamlines. Now more as to end a little bit this, I only talked about diffraction, work made at this beamline 3. There are 17, quite a few diffractometers, but many other instruments that can help different cases of science. And within Oak Ridge, we have 12 other Neutron beamlines at this HIFER reactor. Now, for the community in Latin America, we do have, as I said, a completely open proposal call. Mario and I collaborated with several proposals, both at SNS and HIFER. He does know that in Porto, people have sent proposals. Many times that they weren't here even. We do, if you have ideas, we do have collaborative development that allows you to basically reserve time for up to 3 years if there's like a real interesting project that we believe is also useful for us. We do have many beamlines with mail-in, so you can be in your lab and send us your samples, and you can do both PDF measurements, diffraction, and also some inelastic measurements. Typically, those are limited to 1 day. We can also try your things. That's kind of for free. You just send us anytime if you have a gap in the schedule. We tell you how your data is going to look like to kind of in preparation for a general user. And if you have something really exciting, just call me. We do have discretionary time. It's about 25%. So at any point, we can try to schedule without having to wait for a proposal call. We do have some flexibility. And I say this because, I mean, it's truly exciting. I bring these replacements and the nuclear reactors in Latin America. I think we're really poised to start a really fruitful collaboration. I did attend the workshop for the Brazilian reactor and the collaboration they have with ISIS, and I was really excited to see that was something. And as you develop a user community for condensed matter physics, I speak for all my colleagues here at Oak Ridge, we'd love to work and kind of get a step forward towards that direction. I'd like to finish with these final thoughts, like these 3 questions that I hope you take something. Like, I do hope that those that didn't know that neutrons do have very unique properties that do allow you insights in very unique characteristics of materials, and do remain valuable despite their history of like decades, and despite the advance of synchrotrons and calculations, they're still a reliable tool. What can we do? We certainly can do more than yesterday. The developments are going, and we are moving forward. We have much smaller beams than we did certainly 5 years ago. We can do faster measurements and stroboscopic measurements. We are now demonstrated 100 GPa just to talk about pressure. We can levitate samples and melt them with lasers. We can do multimodal measurements, for instance, doing catalysis with inelastic Newton scattering and mass spec. So we are really vibrant, but we need your ideas to keep going. How does this help you? We do explore new phases. we do have valuable insight in the structural and dynamic behavior from the atomic to the real space. Our most neutron instrument, the most new neutron instrument, is an imaging instrument which is energy resolved. And finally, going back to the ability to calculate, this should help you provide valuable data to validate and improve theoretical models. This is actually one of the most recent collaborations, very fruitful, between Mario and me and YQ, a colleague of mine, that we actually coupled some of the neutron data from SNAP with an idea that a mean field model that Mario had, and kind of brought it together to make a nice work that was recently published. And with that, I just say muito obrigado. This is an aerial view of our facility. You can see we're still surrounded by woods, just like we were in World War II in the 40s. But it's beautiful. And in case you didn't know, for the first time since I've been here, there was a sunstorm, and the Northern Hemisphere has been seeing like the Aurora Borealis. And it was seen in Tennessee, and I think it was seen in Portugal as well. So tonight I'll try to go out after dark and see if I can catch a glimpse of this phenomena, this Aurora Borealis in the heat of Tennessee. Again, thank you for your attention, and I hope there's some questions that I can help with.
Antonio, thanks for your talk. I will pass for the questions time. And first, Luis, I think you have time restrictions, so I will pass the words for you. Luis, if you have some questions.
Oh, thank you, Mario. Yes, thank you, Antonio Santos, for your nice talk. Very interesting, yes, very impressive as well. There's a lot of applications and so on. Very powerful, yes, facility. Well, I have one question about you mentioned that for measuring their applied magnetic fields.
Yep.
In that case, also we can apply, or we can decrease the temperature, right? And if it is, we increase the temperature, or what will be the conditions of the sample? Can be powder, can be bulk, or can be thin films? And if I suppose that the beam will pass over the sample, so, or could be also by reflection or transmission, or what will be the conditions, and also if you can give us information of until how how strong I can apply the magnetic field, and up to what temperature I can decrease the temperature, of course. Thank you for your talk.
Hi. Thank you for your question, Luis. Now, there's a lot to unpack there. So we do have many magnets. Now, of course, to go in diffraction is not really a transmission because you're confined by Bragg's law to some scattering angle. Now, we do have magnets, I believe, at 5 Tesla for a small angle neutron scattering. So you can go in transmission and say, in your case, because from your question, I understand, you can say like magnetic vortices, and they have been studied with sands to see large magnetic structures, skyrmions, for instance. Sorry, I meant skyrmions, not magnetic vortices. Well, those two. But if you have really long range magnetic structures, you can study with sands up to 5 Tesla. Most magnets are compatible with a helium-3 stick, so you can go to like at least hundreds of millikelvin, certainly below 1 Kelvin on all the magnets. Your other question, the powders or single crystals or bulk, it's really a lot to unpack. Well, it's not that much to unpack. All of it. Now, it is true that if you want like a dispersion curve, like I showed for the graphite, and you really want to see magnons like that, you can't use powder. You need to have a single crystal to orient with respect to the incident beam. There are other techniques, like for instance, like some that I do with Mario, like magnetic ordering, where, yeah, just powder diffraction, some metamagnetic transitions. I did that work actually recently with a Brazilian colleague, Fabiano, and he was trying the metamagnetic structures of holmium. And that was a chunk of polycrystalline holmium. And when you just apply up to, in that case, 3 Tesla, the magnet could go to 5, but that's all we needed. No low temperature. So we can do like that. We can do many things. And it really depends a lot on what you want to learn, right? from what I understand, the biggest magnet we're now commissioning, which is not compatible for all instruments, but it is compatible for some, is a 14 Tesla magnet, 1.4, DC. So it's a DC magnet. We have demonstrated, but it's not for users. It could be a collaborative development, a pulsed magnet for neutrons, and they went to over 30. So there are neutron measurements with us for over 30 Tesla in pulsed magnet. Now, you really need to know much more about your sample because it's you have much less data when you're pulsing a magnet like that. For your final question, reflectometry, yes, that is okay. There's a specific instrument for that. It's called a magnetic reflectometer. It does have polarized neutrons to really see because the samples are small, to get much more sensitivity to the moment and the direction. It does exist. I believe they have 5 Tesla magnets. They have at least a 1 Tesla permanent magnet. It then depends what they want to measure. If you want a fully polarized measurement of the interface, you actually don't want to apply a strong magnetic field. So, now if you do have a heterostructure and you want to polarize with field, that does exist as well. But it's a very specific instrument. And they have tried, and to be honest, I'm not sure how successful it was, to grow a thick curve film and go to a single crystal diffractometer to see if they could just see that bulk. But of course, then it really depends. I'd love to talk with you if you have a specific idea. But yeah, we do have fields. We go to like millikelvin temperature. We go to 14 is the maximum. I think the standard is like 7 or 5, something like that. That does rotate for diffractometers, inelastic, everything. And we can do SANS for large structure, magnetic structures. We can do diffuse scattering. There's a specific beamline for that. We do magnetic PDF. So if it doesn't really coalesce with a Bragg signal, but you are just trying to see the kind of the local magnetic exchange. Like I've worked some with people in Porto on Griffiths phases, like some nano domains that don't really develop into a full-on magnetic structure. You can do that from magnetic PDF. So I know it's a lot to unpack in my answer, but it was a big question too. So I hope I answered a little bit.
Okay, thank you very much, Antonio. Thank you very much for your nice talk. Thank you, Mario.
Okay. Stuart Holmes from UK. Do you have any questions for Antonio?
Thank you, Antonio, for your fantastic talk. I just have a couple of questions. One is more a kind of a general question, and the second is a more technical question. I mean, recently we hear about the high temperature superconductors, the hydride materials. You put on a few kilobars and they go superconducting. Have you ever looked at those materials in your system?
Yes and no. So the yes, we have tried some analogs of like large hydrides, like yttrium trihydride, lanthanum trihydride, as like proxy systems. When there was I presume I can say this without fear of retribution, the now debunked claim of basically few kilowatt superconductivity that has been debunked. They did try to measure, and we did see Bragg peaks from something that they brought. Now, why is it difficult? It's because many of these phases, they're called superhydrides, and they form you go to fairly high pressures, and then you laser heat. The problem with laser heating, and that is the problem with that whole field a little bit, is a challenge. Like I said, a challenge is an opportunity. But when you laser heat, and that's true even in the synchrotrons, which much more smaller samples than for us, you always have a mixed phase. So you may have multiple polyhydrides, and sometimes you start maybe reacting with if there's a solid source of hydrogen like ammonia, you can have like nitrogen incorporated in the structure or other things. So figuring out which, even if you measure superconductivity, like they did, by the way, like nobody disputes the results of almost room temperature superconductivity at 200 GPa. Those are fairly, or over 100. Those are, I think, established. But even those were laser heated, and for a long time they were like trying to resort to first principles calculations to understand like what is the hydrogenation level, because X-rays won't tell you the hydrogen location or amount, so they had to kind of like infer from the lattice parameter of the heavy atom, how many hydrogens would fit at that density. So yes, we did try to do that. That whole field, the really low pressure was a little bit debunked over the last summer or so, summer this year. Yeah, it's a work in progress. The other thing for the application, Stuart, just to like say, is that because hydrogens play such an important role in multi-hydrogens, for neutrons you kind of want deuterium, and that will shift those superconducting transitions. Like, to the best of my knowledge, you don't create or suppress superconductivity by the isotope difference, but I would suspect that, especially when you're talking about like tens of GPa, those phases may change with significant pressure, depending if you use the deuterium for neutrons or use the natural in your lab for regular measurements. So,
thank you. The other question I have was a technical question, and that is how you measure the pressure. I assume you either use a Ruby, or do you have some in situ shift of a peak or some splitting? Do you have an in situ measurement, or do you just rely on the Ruby to measure the pressure?
Depends on the pressure cell. So for the diamond anvil cell, we do have Ruby measurements. The bigger, I'm going to be very frank because we're among friends, like the biggest challenge is that when you go to a synchrotron, you have what they call a double membrane that kind of monitor, because we have a lot of sometimes more than 1 ton of load on these presses. And as you cool, just like differential thermal expansion can vary the pressure like multiple GPAs. So for instance, we find it really challenging for these like quantum systems that you really want to keep it like 2 GPa. By the time we're at 5 Kelvin, we can be like at 8 or 12, and then you kind of missed it, right? So it has been a challenge, the temperature stability. I'm talking about the diamond anvil cell. There is a development, I think it is published, where we put like a Ruby on a clamp cell, but not all instruments can have it measuring in situ when it's cold. So it's basically you just measure it when you change pressure anyways. And the clamp cells, we do add an internal standard, which is basically put lead powder or sodium chloride powder with a sample. And then we just try to go from an internal standard if we can. Because we do work with a lot of a priori work, like nobody comes to the neutron pressure without doing any other pressure measurement. Very often we have the equations of state from X-rays, in which case we can just use the sample as our internal standard to then define the error bars, or define the pressure that we're measuring.
It's very comprehensive answers there. Thank you, and a fascinating talk. Thank you, Antonio.
Thank you, Stuart.
Thank you.
Thank you, Stuart. Well, Arturo from Mexico told me that has no questions. Thank you, Arturo. Maggie from Sanchez from Mexico, do you have any question?
Hello, yes, good morning.
Hi, good morning, Maggie.
Thank you very much for the presentation. When I was doing my PhD, I used to do science in ISIS and in Grenoble, in the low-Q and the 22, but that was more than about 20 or something years ago. But in surfactant systems, like in micelles, microemulsions, and so on. Right now, I'm starting to work on metal organic frameworks. I'm just starting to in that area, and these systems are very important for they have many applications, but one of the applications is like the interaction with gas, like hydrogen storage, CO2 capture, and you have shown in the possible applications the characterization of guest host systems. So I was wondering if I mean, in talking about the high pressure systems, have you done in your facilities this kind of experiments, like MOFs with these gases?
Of course,
and then if it can be in the MOF, can we analyze in such conditions powders? If the MOF can be a powder or you know, like a continuous structure, like a foam or single crystal? What kind of sample can we analyze there?
Well, we have measured at SNAP and many other beamlines. I mean, in fact, the types of pressures that for these types of complex structures are needed, they're, let's call, trivial, which is a good thing for you because you can have panels, maybe like just a few hundred bar, that can really go and measure at any beamline. So I can give you several examples of things we've measured. No, the bad news will come soon, okay, Maggie? So don't get all excited yet, but we can measure, for instance, not only the structure. I have a paper from a colleague that did use the CO2 location in a moth because it was breathing. So as a function of pressure and temperature, some cavities would expand and allow the CO2 to go in, and then it would be locked in again. And then we could compare that with nitrogen, for instance, N2, and see how the same moth would respond to different gases in a structurally different way. So that was, you could see the contrast, the CO2 contrast inside those cavities. It is challenging because they're very extended lattices, but it's powder. So if you can do it powder, you do. You can also do, in basis or vision, there are more inelastic measurements that allow you to see the dynamics of the gas as it's in that cavity. Is it rotating? What is the height of the energy barrier? What is the diffusion coefficient, if you want to say, used as a catalyst? So you have the flow of gas through a porous system. So that's not diffraction anymore. Now we're looking at more the energy time like axis, right? So you can do that. There are instruments that measure that. So yes, the question is yes, we have measured the inelastic portions of it, so how the gas behaves, and also the static, where it is under the crystallography. Now the not so good part is that that work with CO2 is with an F moth, which is actually a very, very highly fluorinated moth. And so it really depends how applicable is, like, how do you dominate your chemistry? If you can make a deuterated analog, or if it happens to be a moth that is basically based on low hydrogen content molecules, you are much more likely to succeed, right? Some of the moths that people bring or show, there some is maybe like 3 hydrogens per any other atom, and the incoherent scattering of hydrogen, as you know, obviously, would really dominate. But so the question is very positive from the actual technique side. Yes, we can give up to, well, soon we'll do up to 10 kilobar of gas, but we can certainly have devices that go 2-3 kilobar, and you can do things you can do in flow, anything you want. We can do the diffraction. We don't need we don't need single crystals at all. Depends on the detail, obviously, but if you want, like, just basically learn how much absorption you have on the cavity, the occupation factor, I think powder should be sufficient. But yeah, we do have many people in the moth community. There's that barrier to entrance because you do need to control the chemistry in a way that you can, we may help you to deuterate, but it needs to be done. Many of these systems. And if you email me, I can then email back to you one of my collaborators that did some of the bigger work with modeling of neutron phenomena on these, like, more extended lattices. So you can see which instruments he used and what he was eliciting from it.
Okay. Thank you very much. Yeah, actually, I'm doing some fluorinated MOF, so maybe there is.
That is perfect then. Reach out outside and then we can talk further.
Thank you very much.
Thank you.
Okay. The next one, I'm sorry, but I don't know the country of Laura Mesa. Laura Mesa, do you have any question to address to Antonio?
Professor Mario Reyes, Laura Vanessa is a student from National University. She is helping me with all about this in our.
Good. Okay, yes. Good. But Ximena, okay, do you have any question in the students broadcasting?
No, in our case, we don't have any question from our university. The people only say thank you for this interesting talk. No, and in my case, I don't have question. That is an interesting work. Thank you for your talk.
Thank you very much.
Thank you, Ximena. Thank you, Ximena. James, the same. Do you have any question from your side? And I think you also handle people from the broadcasting, right?
Gracias, profesor Mario, por pasarme. Saludos, profesor Antonio. No tenemos preguntas como tal, solo comentarios y felicitaciones por su presentación. Gracias, profesor.
Thank you.
Okay, I think you have addressed all of the panelists. Is also my final comment. I'm a witness about the collaboration with Antonio. We have shared one student. I have sent also students for a short period of weeks several years ago, and also sent samples to measure there in this Neutron facility with Antonio, and the collaboration works pretty well. It's very easy to work with Antonio. He's a great guy and a great scientist. If you have the opportunity to work with Antonio, you'll see that's a very easy collaboration. It's a great opportunity for students here in Latin America to access this great facility there in US. Well, Antonio, if you have final words from your side, I don't know if you have some final words.
No, just thank you all for your attention, both in the panelists and the people on the other media. And I really mean it. I do look forward to keep the collaboration with Mario. And I'm really happy that to get access to this platform, because maybe I'll keep my eye out for the next few Saturdays to know the other interesting things that the network is working on. And I know that last year, I believe it was last year, right, Mario, the conference in Peru. And
yes,
yeah, so I really look forward if such an event happens in the future, that I have the opportunity to join in and see you all in real life and learn from you all and help what I can.
Okay, thank you. So let's open the camera to say goodbye. Okay, bye-bye.
Okay.
Have a good weekend, everybody.
Bye. Bye.
Bye-bye.
Bye. Bye.
Bye-bye.
Hasta luego a todos.